Welcome to the Moving Beyond Earth Gallery, and especially to the What's New in Aerospace program that we've been hosting here now this year and are very excited about. We also want to welcome our electronic audience, the NASA Network audience, and talk about a subject which actually is very dear, I think, to my heart, and that is underlying all of this, is there life in the universe? Well, the answer to that, what would you say? Who would like to answer that question with a one word? Is there life in the universe? Just blurt it out. Yes. Where is it? Here. But now here is to find it elsewhere. And we have two great speakers today. We have Tom Barclay, who is from the Area Environmental Research Institute, but he is a scientist working on NASA's Kepler and K2 missions. And that means that he finds these extrasolar planets around an abundance of stars. In the last few years, it's just really been exciting that there are so many stars out there with planets. But then what do you do when you find them? Well, we also have Hannah Wakeford, who is a postdoctoral fellow at the Goddard Space Flight Center, and she's working in the Planetary Systems Laboratory to say, okay, once you find a planet, does it have an atmosphere, and is it suitable for life? So it's hard for me to get my mind around the fact that not only are we looking for planets, but we are applying environmental techniques and interpretive studies to these extrasolar systems. And so sooner or later, I think we're going to have an answer. Now, why are we doing this now? Because it's been 20 years since our understanding of are there other planets around other stars and other solar systems in the universe beyond our own. 20 years ago, 25 years ago, we would like to say sure, but we really don't know. Today, sure, we really do know. And that's been a totally exciting thing, and we're going to be looking at the two primary elements of the search itself, and then what do you do with the search in this program today. So I'd like to turn first to Tom, who is going to tell us about that search.
All right. Thank you. So like I said, my name's Tom Barclay, and I'm coming out of Ames Research Center, which is based in the heart of Silicon Valley in California. And what I do is I look for planets orbiting stars other than the sun. We call these planets extrasolar planets, or at least we did a few years ago, but extrasolar is too long, so now we call it exoplanets. So these are planets that orbit stars very distant from our own, stars perhaps like the sun, perhaps very different from the sun, but far out in the Milky Way. Put up some slides. I think I can show you a little bit about the history of finding other planets and how NASA is invested in this search. So the first planets were found, in fact the first planet orbiting a star like our sun was found this month 20 years ago in 1995, orbiting a star known as 51 Peg. These were found from the ground, but since then NASA's been spending most of its resources and time searching for planets from space, using space telescopes. This started with the great workhorse of NASA, the Hubble Space Telescope, which is very famous for its beautiful images. This started this revolution, but it's Kepler, the Kepler Space Telescope, this telescope I'm going to discuss in a little bit during this talk, that really changed our understanding of our place in the universe. And going on from there, there's the K2 mission, which is Kepler's new life, and in the future, something known as the TESS mission, the Transiting Exoplanet Survey Satellite, which for those of you in this room can learn about it after this talk at the back here, and following up with NASA's next great observatory, the James Webb Telescope. And then beyond that, there are probably what some of the kids in the audience are going to be working on if they become scientists. So with this talk, really what I want you to do with mine and Hannah's talk is by the end of it, know how we're going to hopefully find aliens. That's the plan. So if you stay till the end, you should know how we're going to do this. Now make no mistake, the people who, perhaps 20 years ago, who said they want to go and find aliens, they were they were thought of as a little bit crazy, but now this is real science. Real scientists are thinking really hard about how to find life elsewhere in the universe. So the way we find planets with a Kepler spacecraft is using something we call the transit technique. The way a transit works is you have a star and you have a planet pass in front of that star. That planet blocks a little bit of the light coming from the star. The star gets dimmer to our spacecraft. It appears dimmer because some of the light's blocked and we know a planet is there. We're fortunate enough to see planets in our own solar system transit the star. Just once every about 200 years, Venus transits the sun from our perspective. But fortunately, we're living in a time when that's just happened. So if you missed it, well, I hope you're living a healthy life because you're probably going to need to live at least another 200 years to see another one. But in 2012, Venus transited the sun. This here is a video, for those of you who can look left or right who are in the room, of the transit of Venus. You can see here the planet slowly moving across the face of the sun. And you see the sun here isn't of uniform brightness. It's not one flat disk it appears to us to be. It's actually very active and dynamic, and a lot of things are happening on the surface here. You see near the edges it appears dimmer to our eyes. You see as it repeats the planet coming in across the limb of the star, the dimmer part. You see there's actually lots of stuff going on the surface. This is convection, this is hot plasma, hot gas moving up and moving down as the planet passes in front of this star. This is actually, in our spacecraft, what causes us our noise. Our detection is limited by how much stuff is happening on the surface of the star. So this is what we do. We take the light of a star, we sum it all up, and we wait for a planet to pass in front of a star. Here's more of a real data. This is what our spacecraft takes. Now, many people won't show real data because it's a little bit more difficult to interpret. But what you're seeing here is a time series. So we measure the brightness of a star every 30 minutes. And in this case, every few days, you see a regular dip. This regular dip is because a planet's passing in front. And by the depth of the dip, you can tell how big the planet is. That's simply because you have a bigger planet, you block more starlight. You have a smaller planet, you block a tiny fraction of the starlight. And by how often the dip happens, you can tell how often this planet goes round the star. We call this the orbital period. So what's our orbital period? Does anyone know how often we go round our star? We've got a simple word for it. It's called a year. 365 days. That's how often it takes us to go round. We know of planets that go round their star in just 12 hours. We know other ones that go round their star in centuries. There's a huge range of years, orbital periods for other planets. So in order to detect these transits, we built a special kind of spacecraft, a detector that is very big. You need a very big detector because you need to look at a lot of stars. Now think of how a transit works. You have a star in the middle, you have a planet further out, the planet goes round in a circle or an ellipse, but you need to be lined up just right to see it pass in front. If you're at the wrong angle, it's angled away from you and you see no planet. So you need to look at an awfully large number of stars to just see one transit. If you were to detect Earth, you need to look at about 200 Earth analog systems just like the Earth, in order to detect one Earth. And that's because the chance of lining up is about 1 in 200. This movie here is showing the Kepler spacecraft we built with this large detector to detect planets. The other thing you need to look at the field for a very long time. So we launched this spacecraft in 2009, and we spent about 3.5 years looking at the same field. This is the field in the sky. You see the Milky Way running through the middle here. And just above the Milky Way, you see this strange pattern that's like a square with the corners cut out. That's the shape of our camera. And the picture here is the photo we took of the sky when our camera went first into space to detect things. And just zoomed in the bottom left here, you see some fuzzy blobs. These fuzzy blobs are stars. This is what we look at. You know, people don't often show data coming from our Kepler spacecraft, and that's because we take images that look like this that to me are beautiful, but probably aren't as beautiful to the public, to you guys. They're not Hubble images. They don't have beautiful colors. They don't have lots of nebulosity and beautiful features. But to me, this is amazing. We take these rather ugly images, we add up the starlight, and we find planets. The way we do this, here in the top left is one of these fuzzy blobs. There's one of these stars that we observe. We measure it and measure it and measure it and can keep measuring it for years and years on end, all the time, waiting for a planet to pass in front. And when it does, this is some real data of the first rocky planet we ever found outside of our own solar system. It was known as Kepler 10b, and it weighs something like 8 times as much as the Earth, and it's very hot. It's a hot world. It's nothing like the Earth, but for the first time we knew that there are places out there that are rocky like our own. So let me take you a little bit into the history of where we are. I think because we've now known of exoplanets for 20 years, many of you in the audience won't have been born when we didn't know of planets, and many of you other people in the audience spent most of their life without exoplanets existing. It's nice to look back and look where we are. Up until around about 1995, we had our own planets in our own solar system, 8 or 9, depending on your view of Pluto. And we had a few other tentative hints that there might be other planets out there. In the early 90s, we found a few planets orbiting these strange, weird, dead worlds called neutron stars that were really nothing like our own solar system, but at least there were bodies of the same kind of mass and size as our own solar system out there. But in 1995, we found the first planet orbiting a star other than the sun. And then the floodgates really opened. This is where we went to from the history. I'm showing a graph here. I'm only going to show like 1 or 2 graphs during this talk, but I think it's important to understand where we are via a graph. So the x-axis here, the horizontal axis, shows the orbital period. This is the year of the planets, how long it takes them to go around their star. And the y-axis here, the vertical axis, shows how big the planet is. So you can see the line of Earth, that's at 1 times the size of Earth. And you can see the line of Neptune, that's at 4 times the size of Earth. And you can also see the line of Jupiter, that's at 11 times the size of Earth. From 1995 to 2009, this is the picture of our solar system. And you can see where most of the planets fall. They're high up, they're at the top of the graph. That means that they're the size of Jupiter. They're big things. Some of them are very close in. They're hot Jupiters. They're nothing like our own solar system. And some of them are very far out. They're perhaps more analogous to our own Jupiter-like planet, which orbits very far, about 5 times the distance of Earth from the sun. And then there was a hint, if you look going into the lower left, that there are some smaller planets out there, perhaps some Neptune-sized things, maybe even things a few times bigger than Earth, but very few. So in 2009, we really didn't know, is Earth special? Are there places like Earth out there that we haven't found yet? Or are there simply very few rocky planets that we know of? This is what happened from 2009 to 2013. This is the revolution in our understanding of our place in the universe. We suddenly went from knowing that not knowing of anywhere that looks quite like our own system, to knowing that there are places the size of Earth everywhere. Most of the stars you look at in the night sky will have planets orbiting them. Isn't that incredible? You think there are planets out there. Perhaps it should have been assumed, why should we be special? But hey, we have life, and life seems pretty special to me. But there are planets out there the size of Earth everywhere. Also, even more incredibly to me, the most common planets we find are actually about twice the size of Earth. This means that there's nothing like these in our own solar system, and studying them and understanding them is a real challenge. We don't have proxies of them in our own solar system. This is the similar plot on a slightly different scale, but just to zoom in a little bit on the Earth region. Earth, remember, orbits its star every 365 days. It's about, it's at the one line here. So we're starting to find tentative hints. These are just candidates, not confirmed planets, but candidate planets that are the size of Earth and orbit on the similar sort of orbital periods. So perhaps there are places out there that are similar to Earth. Now, a good question to ask is, why do we care about Earth so much? What's so special about Earth? Well, as scientists, you really shouldn't take a sample size of one, which is one planet that we know with life, and extrapolate to the entire universe. We shouldn't take Earth as our one sample and say everywhere else out there should be like Earth. But Earth's the one place we know with life, and so it seems like the only place to start is to look for places that remind us of Earth. So what do we know about Earth that we think is special? Well, one is it has liquid water on the surface. All life we know of on Earth requires liquid water at some stage in their development to live. So when we go and look for other planets, we look for places that could host liquid water. We call this region the habitable zone. It's not too hot in that the water will boil off and perhaps you'll have a runaway greenhouse like Venus. It's also not too cold that you'll freeze out all the water and you'll turn into a giant snowball. It's just right. It's the Goldilocks zone. The other thing about Earth is it's just about the right size. If you're too big, you have huge envelopes of gas around you. Like Jupiter, it's mostly hydrogen and helium. There's huge amounts of gas there. And while maybe there are flying whales or something in giant exoplanets like Jupiter, it's nothing like life on Earth. So that's why we look for places that are just the right size, smaller than Jupiter, but bigger than Mars. Mars doesn't have any life. It has a little bit of atmosphere, but not very much. Probably not enough to retain any kind of liquid water, at least for a long time. So Earth's that nice region in the middle between not being too big and not being too small. So it was with great excitement in April of last year that we detected the first planet that's the size of Earth and orbits in this region we call the habitable zone, or the Goldilocks zone, around its star. This planet was Kepler 186f. It's one of 5 planets orbiting a star that's smaller and cooler than Earth, smaller and cooler than the Sun. We call this a red dwarf or an M dwarf star. So this planet, it's the same size as Earth. It orbits in the habitable zone. It orbits a slightly different star to our Sun. It was the first time we've known there are places out there that maybe, with the right kind of atmosphere, could have liquid water on their surface. So this is kind of the story of where we've come from with Kepler. It's a relatively short story given the how long we've been around and how long as humankind we've been doing science. It's very short, the history of learning about places that remind us of home. In 2011, we found the first planet that was Earth-size and was orbiting another star, orbiting a star like the Sun. And then later that year, we discovered the first planet in the habitable zone. It's just a few years ago, just 4 years ago, we found these. Kepler 22b was the first planet orbiting the habitable zone. This planet's a bit bigger than Earth. It maybe a water world, maybe has some hydrogen, helium, gas. Maybe it's difficult to tell. It's certainly unlikely to be similar to our environment on Earth. And then last year we found Kepler 186f. That was a big moment, a big discovery. Then earlier this year, in July this year, we detected the first planet that's approximately Earth-sized and orbits a star like the Sun. This was Kepler 452b. You may have seen this in the media. We were very excited, and so was the media, and it was reported very, very heavily. So what's the difference between, and why are we excited both about Kepler 452b, this is this planet orbiting a star like our Sun, and Kepler 186f, the one I showed you a little bit earlier? Well, it's because they orbit very different types of stars, and they're in different environments. Kepler 452b is a planet that's a little bit bigger than Earth. It's about 60% bigger, but it orbits a star like our Sun. So we know there are places out there that are approximately Earth-sized and orbit in the habitable zone around Sun-like stars. Well, that's wonderful. That's absolutely amazing. Now we know that. There's also places out there like Kepler 186f that orbit in the habitable zones of smaller stars. And smaller stars are very exciting because most of our galaxy is made up of small, cool, red dwarfs. About 70% of the stars in our galaxy are made of these small stars. So if we're going to look for life, and perhaps if we're going to look for places out there, the most common planets, the most common places probably to have water are going to be these planets orbiting small, cool stars. So we've gone from knowing that there are planets aren't particularly common, or planets, we know very little about them. Planets are everywhere. However, most of the planets found by the Kepler mission are relatively small, relatively far away, and difficult to follow up. So now we want to build a new mission. NASA's next big mission is known as TESS, the Transiting Exoplanet Survey Satellite. Now we know planets are orbiting most stars. Let's go and look at our nearest neighbors. Let's look at the stars nearby. Stars perhaps we can follow up from the ground, and from other space-based missions much more easily than these faint distant stars we did with Kepler. This is what TESS is going to do, the Transiting Exoplanet Survey Satellite, which will launch in 2017. And so can I demonstrate that? Let me show you what is basically a top-down view with us in the center and then these circles showing you as you zoom out of our galaxy, or zoom out from us, what our local neighborhood of stars is going to be like and how we're going to detect planets. You're going to see several dots here which show in red where we expect to find planets from TESS based on simulations. And then in black, you're going to see where we found planets from Kepler. And you see they're very different populations. So let me zoom out here. All these red dots are TESS. These are the planets we're going to find with this future telescope, our nearest neighbors, ones we can follow up easily. And then you see where Kepler looked. Remember, Kepler looked at one patch of the sky. So as you see that cone coming out from that region from us, where Kepler found all of its planets. So Kepler told us there are planets everywhere. TESS was going to find those are our nearest by. We can follow up and hopefully one day understand what their atmospheres are made of. There we go, this beautiful cone going out into the galaxy. And then on the further out, on the longer term prospects, we're detecting planets right now by looking for proxy methods. We look for planets blocking starlight, primarily at NASA. But what we really want to do is image the planets themselves. Directly imaging of planets. Now, this is something we can do for a small number of giant planets right now. But one day, hopefully when some of your kids are in the audience, maybe in 20 years, we'll be able to image planets orbiting stars, planets that are Earth-size and perhaps in the habitable zone. This is an image here showing you how we directly imaged a planet in our own solar system. This is Cassini taking an image from Saturn of Earth. This is Earth. This is the updated pale blue dot image that was taken a couple of years ago. So with this direct imaging of other planets, we can much more easily study their atmospheres and understand what's going on. But the technology is not there yet, and I'm looking forward to the future, hopefully by the end of my career, when we're going to start to understand these. Okay, with that, thanks.
Well, I'm sure we have some questions here in the audience and also on the NASA network. If anyone here has a question, please come over, and Katie is going to help her with that, but we'll start with the online questions. The online, and I read it, right? Yeah. Why can't I read it? What future projects are geared toward the discovery of more exoplanets? And is the James Webb Telescope able to detect planetary transits? Dustin.
I think I'll address this one a bit. So the next things to detect exoplanets is all about finding our nearest neighbors, finding planets we can follow up much more easily. And you'll hear a little bit about why these planets are special in the next talk. James Webb, while it could detect transits if we wanted to, James Webb's field of view, where it looks, is relatively small. Remember I said transits, you need to be lined up just right. You need to look at a lot of stars. With James Webb, you don't look at a lot of stars. You look at a few stars. So what we're going to do is we're going to find transits from using TESS and found using Kepler. And we're going to follow them up with James Webb to try and study atmospheres, study light reflecting off these planets, pick the best planets and use James Webb to look at them. So James Webb is all about following up rather than discovery.
Okay, I understand we have another online question, and so far nobody here has come up with a question. What is that question? What must you study to become a person who studies exoplanets? Exoplanet geologist? ? I want to follow this career path.
Well, you can go through a number of different career paths to get to the stage, I suppose, where we are right now. I studied planetary and space physics at university, so I did kind of follow the geologist's path route, but lots of people can do physics, you can do maths, you can go through engineering to follow this kind of career path and really kind of select your way through university and through school to do the sciences and to do the core things that we study. It is physics, it's chemistry, and with the astrobiology as we're doing right now, so we're looking at meteorites for hints at life in those. That's done through biology. So all of the sciences, maths and engineering subjects are a perfect way to pave your field towards these exoplanet studies.
Okay. We have time for one more question, one from the audience. Yes. Yes, sir.
Hi. Recently there's been a lot of news about this Dyson sphere potential thing, or the transits in front of a star. Could you talk a little bit about that?
The question is about Dyson spheres and the infrared detectability of very advanced civilizations that have somehow destroyed planetary masses and distributed it around their stars, their host stars, to collect all the energy from that star in order for the civilization to survive. Have I depicted it correctly? Well, have you been looking for them?
So yeah, in the news very recently, there was this pretty, what was announced as to be the strangest star in our galaxy, and there's a whole lot of strange things in our galaxy, but this is amongst the strangest. What we see is, remember we looked for transits with Kepler, what we saw is a whole bunch of things that appeared to be passing in front of a star, and then nothing. Then 800 days later, another whole bunch of things that appear to be passing in front of the star. And we can't right now explain what's going on. We've got some ideas that it perhaps could be something cometary, or it could have been two planets that hit each other and you're seeing fragments, but it's not clear yet. Now, the reason why there's been discussion of Dyson spheres, these basically a whole bunch of detectors of solar panels you put around a star, if you're way more advanced than we are, is because it looks a little bit about like what you might expect these to look like. I mean, we have no idea what aliens would do, but if you need enough energy, maybe you'd put these around. So, absolutely, aliens is the last thing you should go for. If you run out of theories, then you might reach to aliens. And just because this looks like what that might look like, it also looks like what a bunch of other things might look like, and is almost certainly going to be those things. That doesn't mean we shouldn't keep looking. None of us are in this field, I think, because without us wanting to one day detect life elsewhere in the universe.
That question is a really good segue to our next speaker. And now we're going to turn to Hannah Ruth Wakeford from Exeter, England, Exeter University. And she is going to be talking a little bit more about what do you do with a planet once you've found it.
Okay. Hi everybody, I'm Hannah Wakeford, and I currently work at NASA's Goddard Space Flight Center in Maryland, so just outside of DC. And what I'm doing is I'm looking to characterize these types of planets. Using the Hubble Space Telescope, what I'm doing is I'm looking for water vapor in the upper atmospheres of some of these planets, and really trying to work out what they might be like. So I've got a couple of slides to show you, which is taking you through how we do that, how we detect these atmospheres, and how that informs us about what these planets might be like. So Tom showed you this picture here of the distribution of planets, and they really are some very, very alien planets in there, nothing like we're seeing in our own solar system. And what I'm going to highlight is this region of planets in the top corner. These are our hot Jupiters. Now, they're called hot Jupiters because they are roughly the same size or mass as Jupiter, but they orbit their stars 20 times closer to them than the Earth does to the Sun. That's actually 4 times to 8 times closer than even Mercury in our own solar system. So they have incredibly hot atmospheres. And the way that we look at these atmospheres is by looking at the starlight that passes through them before it reaches us. But because these are such alien worlds, to get them in your head a little bit, I want you to imagine that we shrunk the Earth down to the size of a pea. Now, on this scale, the largest planet in our solar system, Jupiter, would be about the size of a large orange. That's 11 times the width of the Earth. These hot Jupiters, these planets that we're finding, we're discovering, orbiting very close to their stars, are on average 1.5 times the size of that. So about the size of a watermelon. So they're very large planets orbiting very close to their stars, and their atmospheres are being heated by their stars. They're constantly bombarded with the radiation from their star, and they're actually hotter than sitting underneath this engine over here as it takes off. So they're incredibly hot places. Now, when we're looking at these, we're looking at them in transit. So because they're passing in front of their star, what we can detect is starlight that has shone through that atmosphere before it reaches us. And we see something like this on the Earth. This is an image taken from the International Space Station in orbit around our planet. And it's able to look through the edge of the Earth's atmosphere. And that's what you're seeing here. If you look through the edge of the Earth's atmosphere, you can see some of the starlight which has passed through it before reaching the camera. And we are doing the same thing for these alien planets. We're looking for that very small amount of starlight which has passed through its atmosphere before it reaches our telescopes. And to put this on scale, this is a scale diagram of a star that we're looking at and a hot Jupiter, one of these really big planets orbiting it. And around that black circle is a blue atmosphere to scale of what we're able to image. And you can very, very barely see that. But we're able to detect the light that has passed through this very, very small amount of atmosphere compared to the size of the planet. And the way that we do that is in the transit. And what we do is we break up that transit light, that light from the star, into all of its different colors. If we break up that light into the different colors, if we just view it in the blue, we get a measurement of the amount of light being blocked out by that planet. If we then measure it across all of the different colors, the green, orange, red, we can build up a picture of how the size, the relative size of what we're seeing of this planet is changing because different parts of the atmosphere, different things in the atmosphere, like water vapor or here, sodium and potassium, are blocking out that light. So if they're blocking out that light in that atmosphere, it looks like it's bigger. So if we build up this picture of these planets over these different colors, we can get an idea of what is in the atmosphere absorbing that light. So when we're looking at the Earth's atmosphere, lots of beautiful water vapor clouds. That water vapor blocks the sun's light down to the surface of the Earth here, just beyond the red part of what our eyes can see. So if we look at these planets in that region, just beyond that red part of what our eyes can see, and we see that the planet appears to be bigger, then we can determine that there is water vapor in that planet's atmosphere blocking that sunlight, that starlight from us. So this is an idea of what different types of planets might have in their atmosphere across the optical and into this infrared region where this water vapor, and you can see it on these very, very hot planets, is blocking this light. And we're able to detect these different molecules from the atmosphere by how much light they're blocking and where they're blocking it. Now, I've got some examples here of a simulated sunset in the atmospheres of one of these hot Jupiters. This is what the sunset would look like from this planet, because we've measured what the different things in the atmosphere are that are blocking that light. And this is the measurements that we've taken with the Hubble Space Telescope. And this shows us that it's scattering lots of blue light, just like the Earth's atmosphere does. If it's scattering lots of light, then it's going to appear very red in sunset. And it's much, much bigger than the Earth's sunset, which you can see in the bottom corner, because it's so much closer to its star. The closer it is, the bigger the star appears to be in its sky. So you can see all of the colors of the sunset across the disk of the star because it's so close. But here's a really alien sunset. This is a sunset on a planet called HD 209458b. Very fancy names in exoplanets. This is a very alien green sunset because it's got lots of sodium in its atmosphere. So the sodium street lamps that you see outside are orange. This has got sodium in its atmosphere. It's blocking out those colors. So if it's absorbing those colors, you're going to see all of the other colors. And you're going to be seeing these blues and these greens. And again, the Earth's sunset in the corner there for scale. Another really strange planet that we look at, this is WASP-12b, and it orbits its star in just over a day. Its year is just a bit longer than our days here on Earth. It's very close to its star, and you can see it's much, much bigger in the sky. But it's got a very gray sunset because it's a very cloudy planet. There's lots of very, very hot molten material in its atmosphere, which is scattering all different colors of light. So it would be a very gray-scale sunset. And these are the actual data points that we're getting from Hubble. So let's go back to our fruit basket of planets. We want to be looking at these Earth-sized planets. And Tom was talking about these planets which are 2 times the size of the Earth. So our little blueberries. We're also detecting these other planets that we don't see in our solar system, these kind of Neptune 4 Earth-sized planets and smaller. And these kind of go up to about the size of an apple. So this is our family of planets that we're discovering in our galaxy. These Earth-sized ones to these super Earths, these 2 times the size to 6 times the size. And then these Jupiters and hot Jupiters. So there's a huge range of planets out there that are nothing like what we've got at home. When we've got planets in our solar system, we can throw things at them. And NASA are fantastic at doing that. Lob a probe at it, see what we can get. We can't do that with these. So we have to look, what would we expect life to do? What in the atmosphere is going to tell us that there's life? And we're looking at these hot Jupiters where we've got a huge extension of the atmosphere down to these super Earths where they're much smaller. There's much less atmosphere. So it's much, much harder to do because less light is able to pass through that atmosphere compared to these really, really expanded planets. So we've got all of these telescopes at our disposal. And in the future, TESS is going to find us more and more of these planets that we can follow up, as Tom said. And James Webb Space Telescope is going to allow us to characterize these, look at their atmospheres, and see what they might be made up of. So, back to our old Voyager 2 pale blue dot. This is what the Earth looks like from afar, suspended in a sunbeam on a mote of dust. If we were to look at what the spectrum, so look at what the absorption, what things are blocking that light for the Earth, we see something very much like this. But what does that mean? We want to know what each of those different lines mean. What is blocking that light? And you can see that there are lots of different parts of the atmosphere where there are different things contributing to it. So this vegetation causes a very specific wavelength, very specific color signature in an atmosphere. The ozone and oxygen, the amount of water vapor we have in our atmosphere. Then there's methane and outgassing from volcanoes. We can look and see if we can find indicators for a balance, an off balance. So we produce, and the cows produce a lot of methane. That is not equal to what would naturally be there. So we can look for these changes, these things that are not in balance. And what kind of life are we talking about? Life is incredibly resilient. It will try and try and try wherever it can to exist. The type of life we're likely talking about are these extremophiles, these things that live in the worst and most harshest places you can imagine. They live in very, very salty places. They live in very, very hot places, cold places, underwater, in pressure environments. The picture in the bottom corner here is of blood falls in Antarctica. This is because subsurface biological material is growing underneath the ice and then is pushed out. It's a different color. It's a different type of life from what we expect. And there's this one really special one called the tardigrade. He's the water bear. And if he was this size, it would be absolutely terrifying. But he is incredibly tiny. But he is a multicelled organism which can survive even in space. And they have been shown to last 10 days in hibernation in space. This type of life is incredibly resilient. And this is what we might be talking about. So we really just need to imagine what are the different places life might thrive, where might we want to explore next. We've got beautiful travel posters for Mars, Titan, the largest moon around Saturn. It's got a huge atmosphere. It's got a nice thick atmosphere where if you flapped your arms, you might even be able to fly. Europa has a huge surface of ice, but underneath that is likely liquid water. These type of very strange organisms might be there. We don't know. But then also think about these exoplanets that we're discovering. Think about these really strange alien worlds, what we can learn from their atmospheres, and where we might be going in the future. Some of you might be the ones that are here to discover that exo-Earth, and some of you might be the ones that are able to build us the instruments and the ships so that we can actually live out these travel poster ideas. But we need the future, and we need the engineers and the scientists to be working on this. And there's so many things that we can answer about ourselves and about our own solar system. So thank you. Any questions as well?
I'd like to start with a dialogue, or maybe a trialogue, between the three of us about this incredible set of perspectives. I mean, 20 years ago, we couldn't have possibly had this conversation. And what was it that made a difference, not only in detecting planets, but in characterizing planets, or being able to characterize the environments for life? And I'm just wondering from both of you, as you trained as students and scholars, what was it that excited you most, saying you can make a contribution to this field? Now, so it's a sort of a complex question. Why couldn't you do it more than 20 years ago? What happened in the last 20 years that changed things? As I know, astronomers have been trying to find planets around other stars for much more than 20 years. And I know for sure that they thought that they had found a few planets, by 1950. And yet all of those planets that they thought they found, only 2 of them, of course, at that time, they didn't turn out to be real. And now we have thousands. What happened in the last 20 years?
Well, 20 years ago, I couldn't have done this because I would have been in first grade. But what's happened is science fiction is now fact. We didn't have these planets before. Science fiction didn't even come up with hot Jupiters. They're so strange we couldn't even imagine them. And we've really been discovering these and discovering what imagination can stretch to at the same time. So when I was doing my studies, I didn't even know about exoplanets in high school. They'd obviously been discovered, but it wasn't part of the curriculum at all. And now it is. Every single child that's being born is born into a world where these planets are known and they exist. And that didn't happen 20 years ago. Mm-hmm. And they're being taught, and that is so important. It's so important that they are being taught in schools, and people know that, we can place our solar system. We're trying to answer those big questions, and science is actually able and in a place where it can actually contribute to that. So as I was coming through university, I went, that's really cool. I can actually do what they do on science fiction. They're going to other planets. I'm going to see if they're going to places that can exist. And that really excited me.
Marvelous. What's your experience?
I think one of the reasons why we can find planets now is because a small number of pioneers 20 and 30 years ago dared to believe that there were planets out there and risked their careers and their reputations, and also spent most of their life not finding planets, but believing they're out there and just willing them to exist. And then they were found. And then once they were found, all of us can ride that wave of there being plenty of interest, and NASA's interest, and the government's interest, and the National Science Foundation supporting this work. But without those people telling us that these studies would reveal something, believing it, we wouldn't be where we are today.
But what were the technologies that made a difference? What was not available more than 20, 30 years ago that is available now? Not only the technologies, but the mindset, maybe. Do you have some sort of view on that?
Certainly technology improves, that's without a doubt. But I absolutely think it's the mindset and the will to do this. There were people proposing missions that would have detected exoplanets way before they were detected. But there wasn't this belief that they'd find anything. They thought it was too risky. Once we knew they were there, then we could take the much smaller risk of building these very expensive missions to find many, many planets.
Okay. Question from the audience.
In terms of the spectrography used to identify exoplanets, does all of the data come from the visual spectrum? And if it doesn't, which part offers the most insight into what the planets are made out of?
That's a really good question. So he asked which part of the spectrum, which part of that color spectrum is really important and which part will give us most information. At the moment, we're using the Hubble Space Telescope, which does have the optical, but it also has this near-infrared part. And that's from Wide Field Camera 3. And if you're here today, you can go outside and see its predecessor, Wide Field Camera 2, which is used to look at the infrared part where water absorption occurs. So most of my PhD was using that to look for water absorption in the upper atmosphere. If we want to go further into the infrared, we're using Spitzer Space Telescope to do that. And Spitzer has 2 bands in the infrared, which we are able to look for these different things. But what James Webb is going to do, so the James Webb Space Telescope, which is going to launch in 2018, that's going to give us coverage from the optical, the end of the red end of the optical, all the way up to 30 microns, and that's well into the infrared, so this heat signature that we've got. So that's going to really expand our understanding of these atmospheres, what is absorbing them in this very, very critical region. And we might even be able to tell you a little bit about what kind of clouds we're looking at.
We have a question from the online audience, and that is, based on your size orbit chart, Earth looks to be a complete outlier. Is this an indication of current technical limitation of observation? John.
I would say it's very likely a limit of observations. I can't say that for sure because we haven't truly found anything we would say is an Earth analog, an Earth twin. Nothing out there quite yet would fulfill that. But it's because of technical limitations. In order to find Earth, you'd need to look from the right angle at the right star for years, several years on end. And then you'd be able to have to model what your spacecraft's doing during that time and really develop your algorithms in order to be able to detect these tiny, tiny signals. So this is something we have been doing with Kepler. Kepler's main mission lasted about 3.5 years, and the time since 2013, the last 18 months, we've been really working on improving our understanding of how the spacecraft is working. It's in space, so you can't go and measure how something reacts to temperature. You have to remote sensor it. So we're improving our remote sensing, we're improving our models of how the spacecraft works. We're trying to understand what the onboard things are doing and what's coming from the star. That's helping us to improve this.
You might talk a little bit about bias. And I don't mean bias in terms of our opinions, but our bias in terms of the fact that we tend to discover planets going around other stars in very short periods because we're not looking for very long time. You had brought that up. But I think you need to emphasize that short period transits, short period variations in radial velocity are more sensible than long period that take longer to discover. And we've only been doing it for a few years. 20 years is not much in at least astronomical time. Do you have any thoughts about that?
Well, as you said, it is much easier for us to detect these big planets. The bigger the planet and the closer it is to the star, the more light it's blocking out. And also at the same time, the closer it is to the star, the smaller its year is. So the smaller the time is between it passing in front one time and coming round and passing in front again. So we can confirm that something is periodically blocking out that light much, much quicker. If it takes 3 days for it to come back round and block out that light again, we can, in a week, tell you that it's blocked out that light a number of times. And that's really important for when we're confirming these. And Kepler's mission was to stare at these stars for 3 years so that over the 3 years you can build up 3 transit events, 3 periods where it's blocking that light for these much, much smaller planets in these much, much wider orbits. Because we need to confirm that the thing that is blocking out the light is actually going to do it again. So it is therefore kind of inferred to be a planet on an orbit, a regular orbit. So it's easier for us to do these bigger ones. And then at the same time, it's easier for us to detect smaller planets orbiting smaller stars because it's a relative size. So we're measuring the amount of light blocked out by the relative size of the planet to the star. So if the star is smaller, the same amount of light that being blocked out by a bigger planet on a bigger star can be measured. So these smaller stars are very important for these kinds of studies as well, because we're able to get to smaller and smaller planets. But if you want to look at ones where the orbit's longer, you have to look at the star for longer. So it takes a lot of time.
That's why when planets started to, or at least transits started to be observed with Kepler, they called them planetary candidates because they had to wait to see if the transit came back. Isn't that right?
Yeah, that's right. We find the planets that are easiest first, and then we go make it harder. So when we first find planets, we find planets that are big and are very close to their star. And we work on those first, and then we get to the more difficult ones. It's no coincidence that the 2 best planets we've found from Kepler are one that's Earth-size, it's in the habitable zone, but it orbits a very small star. And the other one being a star that is the same size as the Sun, the planet's in the habitable zone, but the planet's much bigger. They're skirting around this edge of where we can find things. We can find bigger planets orbiting Sun-like stars, and we can find smaller planets orbiting smaller stars. Finding the true Earth twin, as we say, is very challenging indeed. And I believe we're going to get there, but it's a lot of work, and we hone our skills where we can do it most easily. The same with atmospheres. We start with the atmospheres of these giant planets, and then once we can do this, we move to the more challenging regime of more terrestrial worlds and probing the atmospheres of these worlds. But that comes later.
I can't wait. Now we have a question from the online audience. Have either of the speakers been inspired in their career paths by science fiction books, TV shows, or movies? Doctor Who, perhaps, given you both seem to come from a certain part of the world.
I was inspired when I was growing up by Stargate. I kind of got that there. Stargate is a show about traveling to different planets. And that really, I grew up in the time when that was on television. So that really, and there's a female astrophysicist on the show, and I was like, I can do that. So I basically stopped saying I can't do that and just went for it, really.
Wonderful. How about you?
I mean, absolutely. Science fiction inspires our discoveries. I think the best example of this was there are books written about planets orbiting two stars. There are several of these. Solaris was a book in the 30s, I believe, or a long time ago. But later on, there was Gallifrey in the Doctor Who universe, and then Tatooine in the Star Wars universe, all planets orbiting two stars. So they said they'd be out there, and a lot of scientists kind of said, well, maybe, probably not. It's very difficult, that environment you can't form planets around. Who knows? Guess what? In 2012, Kepler found the first planet orbiting a double star. This is two stars and a planet going around the outside. We call them circumbinary planets. So this is science fiction predicting science fact, or that's what we're doing. And I think that's the best example. And hopefully there'll be more science fiction that will turn into science fact as we go along.
I even remember as a student being asked to try to compute a stable orbit around two stars. And it had to be, the two stars were very close together and the planet was very far away. But do we have one more question from the online audience? In TESS, is TESS like a larger scale Kepler? Just focusing on closer stars. What can you characterize TESS?
Actually, TESS is more like a smaller version of Kepler in many ways. You know, you can imagine something very big honing in on a small area of space, but if you shrink it down, you can look at a much larger region of the sky. That's what TESS is. You shrink down the cameras from Kepler, but you increase the field of view. You know, you think of a microscope. As you zoom in on a microscope, you get your maximum magnification, but your smallest thing you see. You shrink out the magnification, you see a lot more of the sky. That's somewhat of how TESS works.
Well, I want to thank both Hannah and, Tom, sorry, for a wonderful hour here, becoming, I think, comfortable with all of the planets that evidently exist out there. And I certainly want to thank Boeing for making this program possible, and for the staff here that knows how to make looking beyond Earth, or moving beyond Earth, this gallery, a global phenomenon. So thank you very much for coming. Thank you. Sorry, Tom.